Welcome to Electrochemistry Screencast number 3. So far we've looked at redox reactions in electrochemical cells only under standard conditions with 1 molar solutions and with 1 atmosphere gases. But what if the reaction conditions aren't standard? How do we deal with that? Well, we've already seen this in thermochemistry. If we have non-standard conditions, we determine delta G rather than delta G naught, and delta G equals delta G naught plus RT log Q. Now, we've also very recently seen from electrochemistry that delta G is equal to negative NFE. And if we have naught, like standard conditions, we have delta G naught equals negative NFE naught. If we don't have standard conditions, then delta G equals NFE, and neither delta G nor E are standard. Now, if we combine these relationships, here's what happens. So here's our equation, delta G equals delta G naught plus RT ln of Q. And let's divide the whole equation through by negative NF. And of course, delta G divided by negative NF is equal to E, the potential. Delta G naught divided by negative NF is equal to E naught, the standard potential. And then the other stuff, plus RT over negative NF ln of Q, is the same as minus RT over NF times ln of Q. And if we work at 25 degrees Celsius, which is typical, and then plug in the value of R and the value of F, the Faraday constant, then we get a simplified version of this under those conditions. So in other words, RT over F equals 0.0257, and so we get E equals E naught minus 0.0257 volts over N ln of Q. Note that F is the Faraday constant. It's a known value given on your handout, and N is the number of moles of electrons transferred during the process. And we'll see how this comes into play in an example in just a moment. Quick note, this is called the Nernst equation. So let's give this a try. Here we have an electrochemical cell, and we're going to determine E and E naught. So we're going to get the standard and the non-standard potential for this electrochemical cell. In one half cell, we have a platinum electrode with iodine I2 and iodide I-. In the other half cell, we have a platinum electrode as well, and Fe3+ and Fe2+. Now, quick note, platinum is an inert substance, at least not very reactive, and we often use it for electrodes for that reason. There are other things we can use for electrodes that are inert or are not very reactive, such as carbon. And so this isn't going to be a part of our half reactions. The half reactions are going to be between I2 and I-, and between Fe3+ and Fe2+. And if we try to figure out what's going on in terms of what's oxidized and what's reduced, then we have to look at the reduction potentials table. Fe3+ with Fe2+ happens to have a reduction potential of 0.77 volts. I2 with I- has a reduction potential of 0.54 volts. So iron 3+ is more easily reduced, and therefore it will be reduced. And then I- is less easily reduced, so I2 is going to end up being, I2 is less easily reduced, so I- is going to end up being oxidized. So let's do the calculation for E naught. We write the reduction half reaction, which is going to occur the way it's written, as written. 0.77 volts is the potential for that half reaction. The iodine-iodide reaction gets reversed because it's lower in reduction potential, so therefore it's going to be oxidized. Oxidation is opposite of reduction. It's losing electrons rather than gaining. And the cell potential for that, or half cell potential for that half reaction, is negative 0.54 volts rather than positive 0.54 volts. Now notice the number of electrons gained by Fe3 plus compared to the number of electrons lost by I minus. It's 1 versus 2, so we have to balance the equation. So we double everything. 2 Fe3 plus 2 E minus makes 2 Fe2 plus, and then we add up our half reactions. Also worth noting, when we double this half reaction, all we're doing is making the electrons balance. It does not change the value of E naught. Remember that E naught, the potential for a given half reaction, is a measure of inherently how much that substance, in this case Fe3 plus, wants to gain electrons. If we have more Fe3 plus, it doesn't make Fe3 plus itself want to gain any electrons more or less. It doesn't change the potential, but we will see that having more electrons will show up later in the calculation. So when you do your balancing, you do not change the potential for the half reaction, but if you reverse the reaction, of course, then you reverse the potential's sign. So we end up with 0.23 volts for the standard E, the E naught for this reaction. Okay, so there's our reaction. Here's once again looking at the electrochemical cell. Note that we have non-standard concentrations of I minus, 0.002 molar, of Fe3 plus, 0.002 molar, and of Fe2 plus, 2.00 molar. So if we calculate E, we're going to have to take that into account. So here's the reaction with the E naught. And here are the concentrations of the aqueous species. As indicated, Fe3 plus, 0.002 molar, I minus, 0.002 molar, and Fe2 plus, 2 molar. And notice we already have a fairly high concentration of quote-unquote products, the substance on the right, and very low concentrations of the Fe3 plus and of the I minus. So we'll see if that changes anything in terms of whether this reaction is going to spontaneously go to make go from left to right or not. So here's our Nernst equation, allows us to calculate E under non-standard conditions. Q is the reaction quotient, so it's going to be Fe2 plus concentration squared over Fe3 plus concentration squared times I minus concentration squared. So same form as the equilibrium constant, but not at equilibrium. And then we plug in our values, 0.023 volts for E naught. R is 8.3145 joules per Kelvin. Temperature is 298 Kelvin. That's our assumption if no temperature has been specified. Note that we have 2 moles of electrons being transferred. We saw that previously when we balanced the half reactions. And then the Faraday constant is 9.6485 times 10 to the 4th coulombs per mole. C stands for coulombs. And then ln of 2 squared over 0.002 squared times 0.002 squared, plugging in the concentrations that we start with. And when we calculate this term, all of the negative RT ln of F, we get negative 0.34 volts. Notice that that's more than 0.23 volts. So we're subtracting a bigger number from a smaller number, and we get negative 0.11 volts. Now, note that, or remember, with electrochemical processes, a spontaneous electrochemical process has a positive value. So under standard conditions, this reaction is spontaneous. But under non-standard conditions, the E is a negative 0.11 volts, so it's not spontaneous under these specific non-standard conditions. And that's it for screencast number 3.